things that start the same way, inside your URLs or whatever. So using the first 3 letters of a URL is probably a really terrible idea if you're, going to be looking up everything on CNN or whatever it is. It's all going to be the same. You don't have to pick a hash function. By the way, just to show you, we talk about hash functions and numbers. It's all bits. So if you have something which is a character string, you can go ahead and just go ahead and take that character string and treat it as a number. And if you don't want to just treat it as a number and take something which is a 2048 a character thing and treat it as a number, you can reduce it down to 32 bits or 64 bits by exclusive ORing words together to be able to get a single word. So you want to have something that's relatively random about it, but again, you can take something that's 2048, break it down into words, exclusive OR them together, and get something that you can use as, say, a 32-bit number, and then play with this AX plus B modulo M kind of thing. That was very fast, but again, it's not stuff in the score. So again, everything can be treated as a number, and again, exclusive ORing words together is fast. So there are things you can do on that. But there's a terrible case in which hashing is never going to really help you much. What's the terrible case? If the same value appears a lot. If all of your students are located in California, then hashing based on the state is not going to help you. You end up having 1 million students located in California. You're going to have all these California entries, and and it doesn't matter how many bits you take; they're all California. I mean, talk about a bad pun. It's all the same darn thing. It's not a pun, it's identity. So again, that's a case in which there are things with one value in which, none of these approaches per se end up working well, although I'll be describing something to you soon in which there is an approach that can work well if there's a small number of values that occur a lot. How do you deal with a delete? Well, it's the inverse of insert. So you do a delete, you just see what you can do about removing the value. And again, you can sometimes choose to merge a bucket with its split image. So you have this, again, splitting the mitosis that took place in the bloated bucket. You sometimes can decide that you can merge it together with its split image. When you can do that, when B and B2 can both split inside B, you can choose to go ahead and merge them together. And sometimes you might want to do that. Doing it all the time can end up shrinking things down. And sometimes you can even shrink the directory by half. When can you do that? Well, if your global depth is 3 and your local depth for all your buckets is 2, you can shrink everything down to 2. Right? So that's when you can do it. Whether it's a good idea to do it, right? Basically, when everything's down to 2, you could do it. Shrinking and merging can be a good idea, but you don't want to keep, thrashing back and forth and splitting and so on. So maybe you want to do it, when things get, not just exactly at the edge when you can do it, but maybe you want to go a little bit below when everything's only 80% full or something of that sort to be able to do it, or would be 80% full after you did the merge. So, I mean, I think that this is kind of a really cool kind of algorithm. There's a lot more on hashing and distributed environments and so on that you can deal with, large distributed environments, all kinds of fun stuff with hashing. Hashing is kind of neat. But again, it will not solve that everybody's California kind of thing. So great for equality searches, not great for many range searches unless it's a small number of value. Extendable hashing avoids the overflow pages, except in cases, again, where certain values show up a lot. The directory keeps track of the buckets and it doubles periodically. It can get large when the skewed data, but in general it tends to be good. Uniform distribution is the one case where it's bad. Questions on this? Again, there are emphasis. There are many different access paths that exist. And again, with so much data fitting inside memory these days and opportunities for distribution and parallelism, there's a lot of clever stuff with hashing that exists. Questions? One last access path we'll talk about here. And we're going to talk about bitmap indexes. And we'll start off with the motivation. Suppose that there's a world in which people are paying attention to tweets. Yeah, it seems to be things that people are paying attention to these days for good or for ill. And there's going to be a value inside, which is the retweet value, which is Boolean. What was this particular tweet retweeted? So, we could go ahead and use a B plus tree for things like the user ID and the zip and things like that, and that could end up being good. But how many bytes do we have to use for each record inside a B tree? Well, you should know what that is. For each thing, assuming we're using, say, approach 2, the number of bytes that we use is going to be equal to the size of the search key plus the size of the RID. And yeah, we can do clever things with prefix compression and other things, but let's just go ahead and say it's the size of the key plus the size of the RID, just as a rough approximation, although you can sometimes do a bit better. Everybody okay? So for each thing inside the B tree, we're going to have key plus RID. There's also free space to deal with and other things, but just as a rough approximation, we'll say the size of the key plus the size of the RID. So for each tuple, not counting free space, not counting compression, for each tuple, you take the number of tuples times the size of the key plus the size of the RID. That's the amount of space we have to use in the B tree. We okay? We can play with all the other cases, but that just makes it more complicated. Can we do better? Let's see if we can have some adrenaline. It's a Monday, but let's have some adrenaline injected into this. Let's see what we can do about doing better. With lower storage overhead, suppose that you have an attribute like retweet that doesn't have very many different values. Retweet can have 3 values. It can be true, it can be false, it can be null. It's only got 3 values. Can we have a clever approach that uses less space to represent it and still allows us to look up things and do inserts and updates and deletes quickly? Because space, may not be the final frontier, but it does matter. So suppose that we go ahead and we want to answer equality queries based on the retweet things. And if we build a B tree, we're going to have lots of different things with the same value. Yeah, we could play with the RID list approach number 3. But, it's an odd B tree. You just have 3 long RID lists for each value. You could do it. But looking it up, you're going to have to look through you've got 1 million things, and let's say, half of them are false. Looking up a false, you have to look for 500,000 things. That's not really a great B tree. It's not that great. So what you're going to do instead is there's an approach called a bitmap index. What we're going to do is, since there are 3 values, true, false, and null, we're going to have a bitmap array, 1 for each distinct value. We'll have a bitmap array for true, a bitmap array for false, so yes and no, and we'll also have a bitmap array for null. Okay? So the ith bit in each bitmap will tell you whether or not that value, because there are 3 bitmaps, yes, no, null, true, false, and null. It'll tell you whether or not the value of that bit is true. It'll tell you whether that, the ith bit will tell you whether or not it's null, things like that. But we will need a way to be able to map the ith position of the bitmap to an RID. That's one of the weaknesses of this approach, that has a number of different strengths, but we'll see a way to do that. Let's describe the bitmaps and then we'll talk about the mapping. So here's a table with 1 billion tweets. Seemed a little silly the first time I used this slide. 1 billion tweets. Doesn't seem so silly anymore. The world changes. Here's a bitmap that corresponds to the value yes, it was retweeted. So we're going to have a bitmap for yes. So all the things that are yes are going to have a 1 in position I. So we've got 1 through 100 million, or 0 through, or whatever it is, and there's just going to be a 1 that corresponds to yes, it was retweeted. And there are the ones for no, and there are the ones that correspond to no. And so that is a way of representing this where I don't have to use, it's an index. I can just look up, I want to find only the things that correspond to it was not retweeted, so I just find the entries that correspond to the no. inside that, the things that have a 1. Searching for 1s in a bit string is fast to do. So that sounds like it works, and it's nice. So basically, I can search for the I search through the R-no bitmap, and I find all the places where the bit is mapped to 1, and then I do a mapping to the RID that corresponds to position I, and then I fetch the tuple for it, so I get all the things that correspond to the nose. And I may do index intersection with something else that I'm doing too. So that'll work. So I just find the tuples, the RIDs are that correspond to this. So that's cool. Well, the critical issue is finding a way to map a record ID to a bit position. So here's the general idea. You lay out the bitmap in page ID order. And you've got your 1,000 pages, you'll have the bitmap, the things on page 1, the things on page 2, the things on page 3, etc. What else do you then do? So you need a efficient way to map the bit position to a record ID. Here's a gimmick that sort of works. And again, this is the major weakness to this approach. You assume that there's a fixed number of records per page, because records can come and go. So suppose that I can fit 100 records on a page. And then on page 0, I'll have the things that correspond to, positions, 0 through 99. And on page 1, I'll have 100 through 199. On page 2, I'll have 200 RIDs, 200 to 299. It can correspond to, there are 100 slots on the page, and I'll have, basically, I'll have 100 slots on each page potentially. And I can do that if there is, a fixed size of the records on the page. So I'll just say, I'm just going to have a bitmap, and I'll waste some things if I don't fill in the full number of records on the page. But it's fixed size, and the data comes in, I can go ahead and allocate it that way. So I'll lay out the pages so the page number is sequential and increasing, and I just use modular arithmetic to figure out what the position I is. Okay, so if I have position I, how do I find out what the page ID is? I take I modulo, in this case, 100. If 100 is the number of records I can have on the page. And that tells me what the page number is. So I said modulo, I divide. The modulo is for the slot number. So again, to be able to find, the thing that's in position 5100, I take 5100 and I divide by 100, and that tells me it's on page 51. 5105, it would be on page 51 if the value is 100 in slot number 5. Question?
So this is for a fixed size record, right?
For fixed number of records on a page, which usually would mean a fixed size record, yes. We'll come to a caveat on that, but let's say this works nicely if it's a fixed size record and a fixed number of records on each page. It works very nicely for that. And again, it's saying I'm going to be wasting a bit even when certain things aren't filled in on the page. Of course, then I'll have zeros on everything that correspond to it if I go ahead and do that. Okay, so basically, again, how do I go ahead and find, if I have I, how do I find the RID? The RID is just the page ID and the slot number. I know how to find the page ID, that's divide and take, 4. And how do I find the slot number? I divide and take the modules. And modulo 100 or whatever the number of records on the page is. As we were already talking about, the implications of fixing the number of records on a page is that if I have variable size records, I still have to fix the number of records on the page based on the largest record I can have, or just end up playing games where I waste space. So again, I could end up having underfilled things. If I have one record that's of size 2000, then if I'm going with a maximum of 2 things on a 4K page or whatever the number is, then it means that I'm wasting a whole lot of space on pages. So this is much better with fixed size. You can do it with variable size, but it's kind of wasteful. But it's kind of a neat approach. So here's an example. Suppose that the table is just stored in a heap file, and I have the values with the y and the n over there. So I can have the bitmap that corresponds to yes. I can have the bitmap that corresponds to no. I can have the bitmap that corresponds to null. And using that, I can do my lookups. because I can look up everything that corresponds to null by using the things that are null. I can correspond to everything that's not null by using the things that are either yes or no. The things that are not null are the things that are either yes or no. So I can OR together the bitmap for yes and no. Anything that either has a 1 in the yes vector or in the no vector does not have null. So that tells me what the rules are. How do we handle inserts and deletes and updates? Very carefully, but a better answer is you just go ahead, if I do an insert, and I put things into the bitmap that correspond to the thing that I inserted. If it's yes, I have its bit set to 1 in the yes vector. If it's no, I have its bit set to 1 in the no vector. If it's no, I have its bit set to 1 in the no vector. Okay. And what about an update? If it changes from no to yes, right? It wasn't retweeted before, it was retweeted now. I changed the bit that was 1 in the no vector and make it 0. I changed the bit that was 0 in the yes vector and I change it to 1. As long as I can work out the positions, that works fairly nicely. So again, suppose that I want to count the number of tweets where the retweet is n. I just count the number of n's. March through fairly fast code, just count the ones that are inside that vector. That's pretty easy. And how do I go ahead and select the things where it's not null? It's what I already told you. I can go ahead and I can use the things where it's yes or no. And that works nicely. And there's something that I'm about to suggest which I want to be a little bit careful about. Look at the null vector. Now you see it, now you don't. Why am I doing that?
Similar to our.
Go ahead. Yeah.
Because if there's a 0 in both yes and no, then you know it's automatically null.
That's right, but I'm going to give you a caveat. You don't need to have all 3 of them if you can deduce one of them from the other 2. Everybody's got to be someplace. If the value is either yes, no, or null, then you don't need all 3, you only need 2. Now I'll give you the caveat. If null is a legitimate value that you can have for the retweet, you don't have a good way to distinguish between there being a tuple whose value is null and you're not having filled in record I and it's not being there. So if null means that the record isn't there, then you're okay. But if null is a legitimate value that you can have for it, you can't have 2 meanings for the same thing. So let me again distinguish. If the idea is yes means yes, no means no, that makes a lot of sense. And if null means that there's no record for that thing, then you can do what we just said. You can figure out the value. If the ORing together of all 3 of these things has to be 1, then you don't need all 3 of them because you can figure out any one of them from the other 2. But if there's a 4th possibility, which is that you could have something where there's no record I, and then all 3 of them are 0, because null doesn't mean it's not there. Null means you just don't know whether it's been retweeted or not. Then it's a little bit tricky. So one last time on this. If the ORing together of the 3 vectors has to give you straight 1s, then you can get rid of one of them because you can deduce that 3rd one from the other 2. But if there really are 4 cases, yes, no, null meaning I don't know whether it's been retweeted or not, and a 4th case, which is there is no ith tuple, that's a little bit trickier. You really do need all 3 of them so you can distinguish not being there from being there, but you don't know if it's been retweeted. Okay, so storing this thing, you have 1 bitmap for each distinct value and 1 bitmap for null, assuming the value can be null, or if we're treating that as the value isn't there. So you need to store each bitmap, and you can have 1 file for each bitmap. And by the way, compression of the bitmaps can end up being terrific. You could have, you know, things where you just end up saying, now I have 1,000 zeros, now I have 12 ones, now I have another 2,000 zeros, now I have 3 ones, etc. These things can get compressed like crazy. Okay, so that works nicely. How big is the bitmap index going to be? You're going to have number of tuples plus times the number of distinct values plus 1 for the null, which again, you know, you have to figure out whether null means not known or doesn't exist. Okay, so number of tuples times the number of distinct values plus 1, and that's bits, not words, not even bytes. It's bits. Right? Bit off more than you can chew? I hope not. So when is this going to be more efficient than a B tree? Well, notice that for each tuple, the number of bits you need is the number of distinct domain values plus 1. Whereas what we did when we had a B tree was we said for each tuple, the number of bits you were going to need is going to be the data entry size in the B tree, which is going to be the size of the RID plus the size of the plus the size of the search key. Okay, so the data entry size is going to be the size of the search key plus the size of the RID. So this could be more space efficient, and it's also pretty fast to use. It can be more space efficient, uses less memory, you know, kinder. By the way, in your use of NUMA, L1, L2, L3, when you're scanning through something consecutively, you know, hardware is very efficient to be able to do that. So that's the general idea. So now what we've done is we've looked at ISAM, which was the predecessor, very static, very good for when the data doesn't change, but stinks when the data is changing, going to the left or the right. B trees are good at dealing with that.